Okay, so just a brief review from last lecture. So the first was that abelian Fuchsian groups. So kind of to give like a completely full answer for abelian Fuchsian groups, and it's just every abelian Fuchsian group is cyclic. So abelian Fuchsian groups, they kind of structurally they are very simple somehow. They are all cyclic. And in particular, there is no Fuchsian group isomorphic to Z square, which later on, when we speak about a fundamental group and covering spaces, it will tell us something. It will tell us that the compact torus cannot be achieved as a quotient of the hyperbolic plane by a Fuchsian group. Yeah. Okay. And then after that, torsion-free Fuchsian groups and strong proper discontinuity, because somehow we had seen that it is the strong proper strong proper discontinuity of an action by homeomorphism that allows us to produce covering maps. And then we had seen that somehow the discrete subgroups of PSL2R really correspond to those subgroups whose associated action on the hyperbolic plane is properly discontinuous, but in the weak sense. So somehow we still had to verify or to classify or to find explicitly which are the discrete subgroups whose associated action is properly discontinuous in the strong sense, and the answer is just the torsion-free Fuchsian groups, which in the end are those precisely that do not have elliptic elements, and actually, like given any Fuchsian group, its torsion elements are precisely the elliptic elements. Okay, so that was the second part, and then a little bit about elliptic fixed points. So a little bit of what's the structure of the fixed points of non-identity elements if the group happens to be happens to fail to be torsion free. And then an elliptic fixed point was a point fixed by some non-identity element, right? So not to be confused with like something that maybe one is tempted sometimes to interpret is that elliptic fixed point is a point which is fixed by every elliptic element, and that just doesn't make sense. So an elliptic fixed point is a point which is fixed by some non-identity element, and if so, that non-identity element has to be elliptic. And somehow the main theorem is that the set of elliptic fixed points doesn't accumulate in the hyperbolic plane, which is kind of also for the proof. Sometimes one is tempted to think that it just follows from the fact that orbits do not accumulate in U, but not quite, because there could be elliptic fixed points in different orbits. But okay, so they do not accumulate in U. Which another way of seeing this is that if I pick a point randomly in the hyperbolic plane, it is most likely not fixed by any non-identity element of the group. Yeah. Which somehow is important for when we construct the Dirichlet polygon. Okay, and somehow finally, okay, no, not finally. That all stabilizers inside in a Fuchsian group are cyclic, right? So all stabilizers of points in U bar. So if I pick a point in U bar, and I ask about its point in U bar, and I ask about its stabilizer, but it's stabilizer in gamma, right? Not in the whole of PSL2R, just in gamma. That stabilizer is always cyclic, right? And somehow at this point, the ones for which it is not completely trivial is the parabolic and a hyperbolic and the hyperbolic fixed points. And for elliptic is somehow already established from the fact that the discrete subgroups, from the fact that if I have an elliptic element of PSL2R, that elliptic element the subgroup it generates is a subgroup of a circle subgroup of PSL2R, and discrete subgroups of the circle are all cyclic finite. So somehow at this point the elliptic fixed points are somehow already treated. And finally, it was a result about a Riemann surface structure on the orbit space, right? Without proof. So that if you give me any Fuchsian group, then in this orbit space, well, let's say topologized with the identification topology for this map. Well, it admits a Riemann surface structure for which the projection is holomorphic, and then just a word which is somehow at this point for when if gamma is torsion free, the proof of this theorem is not very hard, because if it's torsion free, then we know that the corresponding action of gamma on U is properly discontinuous in the strong sense. Hence, this is a covering map. And if one just thinks about, you see, like, this is a covering map. So one takes an open set here evenly covered by this projection. So one subset here evenly covered by the projection. So somehow one has kind of the pancake picture here, and somehow here I have like my quotient U modulo the action of gamma, and here of course I have U. Right. So when one considers such an evenly covered subset of U modulo the action of gamma, then one says, okay, so what complex charts can I give it, right? And then I can go with this complex chart to this one, or or I can go to this one, or I can go to this one, etc. Right? And the point is that all those complex charts are compatible, because the change of coordinates is precisely doing something like going down and then going up to another one, which coincides with precisely applying some element of gamma. And the elements of gamma are Mobius transformations, which are by holomorphisms of U. Right? So somehow this for gamma torsion free, this theorem is really not so hard to prove. And the case where it becomes hard is when gamma has elliptics, right? So in other words, when there are elliptic fixed points in U, because then in that case, as you saw, if I take an elliptic fixed point and I project it to U modulo gamma, then here in U modulo gamma, then here that point, so this is elliptic fixed point, then its image its image doesn't have any neighborhood which is evenly covered. And so somehow the argument that works for gamma torsion free breaks for gamma non-torsion free. Yeah, and then that part we for the proof I just refer you to these two books from the bibliography of the course. Yeah, okay, so and then we move to, yeah, because here is, yeah, so here now we move to